friends, welcome back to my brand new channel SPS Tech. As you know, I have created this channel to discuss various topics like cloud, Java, data structures, algorithms, microservices, design patterns, machine learning. So I'll be introducing our viewers to all of these topics one by one, and today I have chosen machine learning. In order to demonstrate machine learning, I have chosen a simple machine learning algorithm which is called random forest. So let's see what random forest is. So let's get started. So friends, welcome to Introduction to Random Forest and Decision Trees. So friends, random forest is basically a categorization technique, which means if you have a large set of data and you want to categorize it into some fixed categories, this algorithm can help you achieve that. It comes under the section of supervised learning. What is supervised learning? Supervised learning is that section of machine learning where you use historical data to train your model and then generate predictions for upcoming data. It's called random forest because it uses a random subset of data to train out decision trees. So that's where the keyword random comes from. And forest because it has a bunch of decision trees to generate predictions. So that is where the name random forest comes from. Now coming to supervised learning. Supervised learning is the most common category of machine learning algorithms. In order to achieve supervised learning, we start with a set of data that we know the answer to. Then we split this data into two sets. One is called the training set and the other is called the testing set. And the general ratio between training and test set is 80-20, or sometimes it is even 70-30. So then we take our training set and we feed that training set into the machine learning algorithm so that it can train. So if input is this, the output will be this. If input is this, the output will be this. This way the algorithm trains itself. And once our model is trained, we evaluate how efficient it is. We use the testing set for it, and then we feed the testing set and we match whether the predictions given by the model and the actual output are same or different. What are the variations? And then we calculate its efficiency. So typically in step number 2, which algorithm we use to train our model differentiates our model from other models. And in this case, today we'll be using random forest algorithm to train our model. There are other popular algorithms as well, like k nearest neighbor, linear regression, logistic regression, etc. Decision trees are the core components of the random forest algorithm. A decision tree is simply a step-by-step process to go through to decide a category something belongs to. So let's understand decision tree with the help of an example. Suppose you have a set of fruits and you want to train someone to categorize these fruits. Your set of fruits contain apples, grapefruits, orange, plantain, and banana. So to teach someone to categorize these fruits, we'll use the features of the fruits. For example, we have the color. Apples are red, they can be green, they might be yellow as well. Oranges are orange, grapefruit can be orange or yellow, plantain is yellow, and banana is also yellow. Also, we have the size of the fruit, which is in this case the length of the fruit in centimeters, and the information whether it is easy to peel the fruit or not. So the decision tree will help train this person to categorize a set of fruits into different categories using these features. So this is how a decision tree looks. As you can see, we have used the features of the fruit to categorize it into different categories. So at the top level, we have used the color of the fruit, whether it is yellow or not. In case it is yellow, we are using the size of the fruit, whether it is long and skinny or not. If no, then it's an apple. We can conclude that. If yes, whether it's easy to peel or not. If yes, then it's a banana, and if no, it's a plantain. And moving to the left side, if it is not yellow, whether it's orange or not. If it's not orange, again it's an apple. If it's orange, it can be a grapefruit or it can be an orange as well. Again, in this case, we'll check the size of the fruit. If it is a smaller than a grapefruit, then it's a grapefruit. And if it's larger than a grapefruit, then it's an orange. So this way, using a decision tree, we can classify a set of fruits starting from the top, moving bottom on all the sides. And when we reach the bottom, we have our fruits classified into individual categories. So we are using a set of rules to classify our fruits into different categories. It's not just for fruits, we can classify any categorizable item into different categories using a decision tree. Now, how do we achieve random forest from decision trees? A random forest is made up of a number of decision trees, each of which has been generated slightly differently. So all of the decision trees don't use all of the features available. All of the decision trees also do not train on all of the training data. And while creating a random forest, we use multiple decision trees and then average out the result. So this averaging of result helps us achieve our random forest from our given set of decision trees. So going back to the fruits example, you can see that we have plotted our fruits in an n-dimensional space here. So the square ones are oranges, the diamond ones are apples, the circled blue are grapefruits, and the triangle ones are bananas. Now if we try to classify these fruits using different decision trees, we get this result. You can see that we have different decision trees which are marking different areas for different fruits. So it is marking the top left area for oranges in this case, whereas in the second decision tree, it is marking the top left area for grapefruits. So basically, decision trees classify the complete n-dimensional space into different categories. And then when we do an averaging of the result of different decision trees, we get the following out. You can see that the area which are confirmed in a particular color are confirmed for a particular fruit. For example, the left bottom area is confirmed for an orange. The right bottom area is confirmed for bananas. The right top area is confirmed for grapefruits. And the area in the center is confirmed for apples. And you can see there is some amount of shaded area as well, which is the case of dilemma. So no machine learning algorithm is perfect and it cannot give you 100% correct predictions. For example, the fruit lying here in this case can be an orange as well or an apple as well. So how accurately your model can predict the categories correctly determines the efficiency of your algorithm. Now, how do we determine what percent of training data should we feed to each of our decision trees? We use the following formula for this. So this formula gives us the percentage of training data that we should be feeding to each decision tree. So for example, if we have 10 items in our training data, if we calculate the percentage using this formula, we get 65%, which means that we can either feed 6 items or 7 items because you cannot feed 6.5 items. So you can choose between 6 and 7 what amount of data you should be feeding to each of your decision trees. Again, for 100 items, if we calculate using this formula, we get 63%, which means that 63 items out of 100 you should be feeding to each of your decision tree. Again, if you try to calculate using 1000 items, you will again converge to 63%. So basically 63% is the converged amount of percentage of training data that we should be feeding to each of your decision trees. So friends, as explained to you earlier, we don't allow our decision trees to use all the features available. So at any branch of the decision tree, only a subset of the features is available to it to classify the data. And for selecting the number of features for a decision tree, we use the square root technique. For example, if we have a training set in which we contain apples and pears, and we have their features as weight, size, color, and shape. So when we try to build our decision tree for apples and pears, since we have 4 features available, each of our decision tree will get the square root of 4, which is 2 features to classify the data. So when we start building our decision tree, we can first choose between any 2 features, say for example, color or size. Supposedly we choose size. Then on the second level of the decision tree, we can use another feature. Since we have already chosen size, we can choose between color, weight. So again, if let's say we choose color. So we use the square root technique. So for example, if our decision tree has 5 features, then its square root will come out to 2 point something. In that, we'll converge it to 2. and we'll allow each decision tree to, use two features for classifying the data. So as you have seen, for each of our decision tree, we give them a subset of data and we give them a subset of features as well. So friends, for generating our random forest, we also need to decide how many decision trees we will be using in our random forest. To start with, more trees are usually better, but then we have to consider how much computing resource is available with us. If you take a lot of decision trees, your computer or your server where the algorithm is running, can get overwhelmed and can get overloaded, the memory can crash, and increasing the decision tree is only true up to a point. After that point, the returns start to diminish. So after this point, adding more number of decision trees will not increase the efficiency of the algorithm. For example, going from 10 to 50 trees will certainly improve the result, but going from 1000 to 5000 trees will not add much improvement and also will increase the computing time. So this is in a way a trade-off between the computing time and the efficiency of the algorithm. This is where the role of the data scientist comes into play, where he has to decide the optimal amount of decision trees to be used in the random forest. So friends, no theory is complete without a practical. So here we are at our Jupyter notebook and I'll demonstrate you the random forest algorithm. So I'll walk you through the code and I'll also show you the output. So as you can see, this notebook contains the code for our random forest algorithm. I'll also like to mention to our viewers that you can find this notebook in my GitHub repository. I'll add the link for it in the description. So here what we are doing, we are importing NumPy as NP. So NumPy is basically a mathematical library of Python. Then we are importing pandas as PD. Pandas is another library which provides us data frames in Python. For people who are not aware of data frames, you can just imagine them as a big Excel file containing columns and rows for all your data. Then we are using scikit-learn library to import the iris flower dataset. So this iris flower dataset contains data for iris flowers which are belonging to three categories, and there are four different features for these flowers. And we will use random forest to try to classify these flowers into different categories. Then again from scikit-learn, we are importing the implementation of random forest algorithm. From scikit-learn, we are also importing a method which is called train test split, which will help us to split our data into training data and testing data. We are setting a random seed to the NumPy. This will help us ensure that we get the same set of random data whenever we run this algorithm. Then we are reading the iris data into our iris_df data frame using pandas.dataframe method. As mentioned earlier, a data frame can be visualized as a big Excel file containing all our rows and columns, so basically our data. So we are calling the load iris method and loading the data available in the iris dataset into the iris variable. Then we are creating iris_df data frame using the pandas.dataframe method, and we are loading the iris data and its columns into a data frame. And we are also loading the results of the data, which means which flower belongs to which category, into the iris_target data frame. So basically, iris_df data frame contains the data for different features of each flower, and iris_target_df contains the result, which means which flower belongs to which category. Just to show you our data, I am calling the iris_df.head. As you can see, it is showing us four features: sepal length, sepal width, petal length, and petal width. So these are the four features of each of our flowers. And we have to write an algorithm which would try to classify each of this flower into different categories. So if I run iris_target_head for the first 100 parameters, you can see it is classifying some of the flowers as 0, some as 1. It will further classify some of the flowers as 2, which means it's belonging to the second category. So basically 1, 2, 3 here are the different categories to which each of the flower belongs. Just to make clear to you, I'm showing you the size of the iris dataset. So you can see it contains 150 entries and each entry has 4 features. So basically it is a 150 cross 4 matrix. And if I show you the size of its target, you can see it is of size 150. So here 150 cross 4 is, each entry of this row where there are 4 features for each entry, and 150 here is 0, 1, 2, 3, which means which flower belongs to which category. So friends, I had created these 2 data frames here just to show you the head of each of these data frames so that you're able to visualize what data is present in our data set. Basically, these data frames created here are just for visualization purpose. Now here the real action begins. I am initializing the data in our X variable and the categories of this data in our Y variable. And then we are using our favorite method, train test split, to split this data into training data and testing data. And since we are giving test size as 0.4, which means that training and testing data in the ratio of 6:4, means 60% of data will be training data and 40% of data will be testing data. So we have created, so X train and Y train is our training data and X test and Y test is our testing data. Now we initialize our model, which is random forest classifier in this case. And then we are asking our model to train itself is using the training data. So we are passing the X train, which are the 4 features for each flower, and Y train, which is the result of category of each flower, into our model.fit method. So now we are passing our training data into our model and asking it to train itself using this model. So here X train and Y train is our training data. So X train contains all the 4 features for each flower, and Y train contains the category to which each of the flower belongs. And we are calling the model.fit method and asking it to train itself. And once our model has trained, we'll try to evaluate its efficiency. So you will pass in the X test and Y test, which is our testing data, to calculate how efficient our model is. So if I run it, you see I get 93% efficiency, which means that it tested the model using this X test value, and whatever categories it found for those data, it compared it with their correct category, which is present in Y test. And the efficiency of this algorithm came out to be 93%. So friends, you must have noted while initializing our classifiers, we didn't specify the number of decisions. So the default value of number of decision trees is configured as 100 here. So this result of 93% which we have received is for using a random forest with 100 decision trees. So if I try to increase the number of estimators here, and let's say if I take it as 1000, let's see what will be our result. If I again train our model and again try to test its efficiency, you see I get a better efficiency. Why? Because I've increased the number of decision trees in my random forest. Now let's see if I further increase the number of decision trees, will the efficiency continue to increase or not? Now instead of 1000, I have increased the decision trees to 10,000. I'll again call the fit and score method. As you can see, now it is taking more time to classify the data, which is evident because it is generating a more number of decision trees and then trying to fit our training data and then evaluate our testing data. As you can see, the efficiency again reduced to 93%. As explained earlier, it is not always that if we go on increasing our decision trees, our efficiency will continue to increase. There is a certain point after which there is no benefit of adding the decision trees, or in fact our efficiency would start to decrease as well. So friends, do check out this notebook from my GitHub repository and try it for yourself to get a feel of random forest algorithm.
So friends, I hope you must have understood about machine learning and specifically about random forest. If you like this video, don't forget to give it a thumbs up. And if you have not subscribed to our channel yet, I request you to subscribe to my channel. It gives me the right motivation to create more useful, informative videos for you. Till then, it is SPS signing off. Take care. Bye-bye.